LP. P is normally a subscript for L. This is a sequence space. P is normally called the index or the exponent. Okay. So today we are going to show that these LP spaces for 1 less than or equal to P less than or equal to infinity is a Banach space. We have already shown it's a non-linear space. Okay. So today we will show that it is actually a Banach space. Today I may not be able to write on the vacuum board because there is an update going on for this vacuum center. So it is not allowing me to do. So I will do it today without using the vacuum board. So I may not be able to write, but in the afternoon, 1 to 2, I will write the. There are 1 or 2 things which you should perhaps know. Is that if you take an element of this small LP spaces, they are sequences. So if you look at the what is called an element X, it's a sequence. Normally we write it as Xn or Xi or Xm. This I that we are writing here, or X, whatever it is, it's called the ith term. If you write Xn, it's called the nth term of the sequence. This I is called an index for this sequence. Now, suppose you take a sequence itself in LP. Okay. So, if you take a sequence in LP, then suppose you call that sequence as a Xi. So, for each I equal to 1, 2, 3, n, etc., each one is a sequence. So, we have some difficulty of writing. So, this Xi is a sequence for I equal to 1 to n, dot dot. So, there is a component, mth component of this sequence Xi. Now, how do we denote it? How do we write it? So, what we do is we write that as X subscript Im. So, it has 2 indices. Index is singular, indices is plural. Okay. So, it has two indices, I and M. So, it is denoted by XIM. That's the notation used in the book. So, what XIM means? XIM is the mth component of the sequence Xi. So, if you fix I, then you get the sequence M equal to 1, 2, 3, Xi1, Xi2, Xi3, Xi4, etc., etc. That's one notation that you have to note here. The second notation here is you may fix M and then you can have the sequence Xi. That means it is the mth term of the sequence X1, X2, X3, X4, Xi, Xm. So these are normally the notations that are used in the analysis course. I don't know who has done analysis course to you, so I don't want to take any risk here because we are in the beginning of the course. So we should be very clear about the the notations, etc. What I wish to tell you is that when you look at the xith component, if you take xi and you look at the norm, this norm of x, that is LP norm of xi, It is summation mod x I m equal to 1 to infinity raised to p raised to 1 by p. Okay. Therefore, the right hand side is a sum of the components xim, m equal to 1 to 3 raised to some power, etc. Therefore, this series will be greater than or equal to mod of one of the terms, okay, xim raised to p raised to 1 by p. That is mod of xim. That means if you take the LP norm of xi, the sequence xi, that is always greater than or equal to the mth component of the sequence xi. What is the mth component? xim. This is something which you should remember because we are going to use this particular inequality, that the mth component absolute value xim is less than or equal to the norm of the sequence xi. If you don't want to put the sequence xi, you take any sequence x in LP, then the mth component mod of x of m is always less than or equal to the norm of x in LP. 1 less than or equal to p, less than or equal to infinity. Okay. So this is an important aspect that you should know it. And one of the reasons why we need the completeness is that completeness is an essential matter for actually sequences, whether it converges or not, or whether know about the sequences in that particular space. So that is why I was insisting that these LP spaces, these are the discrete spaces, and we would like to have its completeness. So we are going to look at the proof of the completeness today. Not a difficult proof, a little bit lengthy, but this particular proof is a very typical proof, and similar proofs will come later. So this proof I would like to do it in a leisurely way, in a easy, not in a very fast way. We do it slowly and try to get the feel of it. Oh, that's one issue which I thought I will let you know. The second issue is that today we are going to have an extra class between 2 and 3. Usually what we do is, earlier I used to do, but I have stopped it nowadays. We take the class at the end of the semester. But what happens is at the end of the semester, you are busy with so many things. Some project presentation, this presentation, and then you are busy with end semester exam. So I don't want to load you at the end of the semester. So what I thought was I will take the extra classes in the beginning itself so that you will have enough time to work with. And just still opening the Chrome. The Chrome is not opening here. So if you have the notes with you, you can open it in your laptop or whatever the instrument you are using. So we want to show that the LP spaces 1 less than or equal to p, less than infinity, less than or equal to infinity is actually a Banach space. We have already shown it's a non-linear space. It's a norm we have shown. It's linear, we know it. So we have to show it is complete. Complete means every Cauchy sequence converges. So what is a Cauchy sequence? So if you take a metric space X, a sequence is called Cauchy if distance of xn comma xm goes to 0 as nm goes to infinity. If you don't like this definition, if you are given any epsilon greater than 0, then the distance between n and xm is less than epsilon. If m and n are greater than or equal to some capital N, which depends on epsilon. That is for large M and N, Xn and Xm are close. So such a sequence is called a Cauchy sequence. Now it is not necessary that every Cauchy sequence should converge. Okay, take the metric space open interval 0, 1 and you take 1 by n sequence. You can show that sequence 1 by n is Cauchy, but 1 by n does not converge in the open interval 0, 1. Actually, it converges to 0 in R, but we have pulled out the 0. So it is not. So this is a Cauchy sequence, but it is not convergent in open interval 0, 1. Essentially, what it says is that the 0, 1 is not a complete metric space. Okay. So this is one thing which you should know. Now, there is a second theorem. I don't know who has done metric spaces for you. A metric space is, if it is complete, suppose you take xd to be a metric space which is complete, and if you look at a closed subspace or a closed subset, then that is also complete. Well, this is something which might have been done in your metric space theory. So one thing that you should note is that every closed subspace of a metric space is complete. Example is that take the closed interval 0, 1 in R, then it is complete because the real line is complete. On the other hand, the open set 0, 1 or even closed open intervals like 0, 1, you close it at 0 and open it at 1. It's not a closed set, and therefore it won't be a complete matrix subspace. So these are some of the issues which you perhaps have to know it, but there is another concept called the compact metric spaces. Fortunately or unfortunately, your syllabus does not contain the compact metric spaces. I won't be able to, do the compact spaces, but it's one of the most essential part of any nonlinear space. What I will do is I will give some 2-3 lectures on compact, compactness in compact operators in your course, but I won't include it in the syllabus. In the syllabus means there won't be any questions coming from there. So for these 2-3 lectures, those who are interested can join. Okay, I am not making it compulsory. So if you want to know about compact operators, I will do it separately. That's the second issue. The third issue is about administrative part of the course. I don't know whether you like quizzes. Do you?
Yes, sir.
Shall I make it surprise? Or you want it to be announced?
Announced, sir.
Hmm?
It
You
will be
want it to be
announced.
surprise or you want it to be announced?
Announced.
Okay. So I will probably have the quizzes on Monday. The reason is that if I have a quiz on some day, then you might bunk other classes and those teachers will curse me. Okay. Is that okay? So I will announce the a quiz on one of the Mondays, and the
Okay, sir.
portions for the quiz that you have to study is just 1 week before. Okay, you don't have to study the whole course. Huh? 1 week before, whatever has been done in the class, you study it. That's the syllabus for that quiz. The quiz will not be more than for 10 minutes. It will be just 5 lines or 4 lines answer. So an advantage is that mm, an advantage of this particular part is that you will you will continuously you will read. That's the reason why I am putting this quiz. Okay, just 1 minute. Huh? So first, let us get some get through some part of the course, and then we'll think of the quizzes. There are many issues, of course. Everybody has one's own way of doing it. Normally, I don't give a quiz for more than 10 minutes. Okay, and it's easy to. If you want weightage in the end semester exam, I'll give you weightage in that. If you don't want the weightage, then I will not bother you. Okay. The My computer has completely gone. Google is not opening Chrome. That's an issue I have.
Sir, if you are facing problems, sir, then you can
Huh?
change the.
Just 1 minute. Huh? Yeah, what you have to talk loudly. Huh?
Sir, am I audible?
Yeah.
Sir, if you are facing problems, sir, then you can take extra classes on Sunday also, sir.
No, no.
Uh,
What I'm saying, it is taking more time. That is all I'm talking about. The screen is in front of me, but Google is not opening Chrome.
okay, okay, sir, no issue, sir.
Just
Then,
wait. Just wait. Huh?
okay, sir.
I'm also opening
Thank you.
Firefox. Let me see which opens. Yeah, Firefox is opening. Okay. Just hold. Huh? Sonu Kumar. It's opening. Just hold. Just hold.
Am I audible?
Yes, sir.
Yes, sir.
Yeah. I'm trying to share the screen. Can you see it?
Yes, sir.
Can you see the screen?
Yes, sir.
Yes, sir. Yes.
Hello?
Yes, sir. It is visible.
Am I audible?
Yes, sir.
Can you see the screen?
Yes, sir.
Which one you are seeing?
Sir, your desktop.
You are not seeing the this one?
Yes, sir. I am seeing this like Foxit PDF Reader installing.
Yeah, it is actually it is installing and it
Yes,
is
sir.
creating stuff.
Yes, sir.
So what I was trying to tell you is that you try to uh, see the I've shared the function analysis. Which one? Can you see function analysis? This one. There's something toxic also. Don't worry about that.
Yes, sir.
Okay. This is what I was trying to tell you, that we want to show this is the theorem 7.5 which I wanted to show, that this LP with LP norm and C0 with infinity norm are Banach spaces. So something more is there, that I'll come to it later. So how do you show that it's a Banach space? We take a sequence, X or Xi in S. This I which I was talking to you earlier, it is the sequence X1, X2, Xn. So for each I, it's a sequence in the sequence space. So how do you write the mth component of this Xi? You write it as Xi m. That's what I was trying to tell you. Okay. So we finally prove the completeness. Suppose Xn is a Cauchy sequence in LP. I'll put it on the top of the page, okay, so that you can see it here. And suppose Xn is then by the definition of the P norm, it is Xin minus Xim. What is this Xin minus Xim? Xin is the nth component of the sequence Xi. Xim is the mth component of the sequence Xi. That will be less than or equal to the norm of Xn minus Xm. So it's ith component of the sequence Xn, ith component of the sequence Xn. This will be less than or equal to the norm of Xn minus Xm in P. This is what I was trying to tell you when I was talking to you on the mobile. This is true for all Im and in the N. So it follows that since this sequence Xn minus Xm is Cauchy, so this is less than epsilon for Nm greater than M. It also tells you that if you fix this I, this Xi, it's Xin, this sequence, if you fix I, you change N, then this sequence Xin minus Xim is also Cauchy. Since the real line is complete, this sequence, whatever this sequence Xi, that will be Xin. The sequence Xi is Cauchy, therefore it will converge. So essentially what we are saying is the sequence Xi converges. So call the, so you define the limit of this particular sequence as Xi. Okay. So the ith component or the nth component, whatever this for a fixed I, so you call this sequence, this being Cauchy, so you let n go to infinity of Xin. What is this Xin? It is the nth component of sequence Xi. So it will converge to some number, call that as Xi. The notation is bad here, okay? So this Xi should have been something else, all right, doesn't matter. Now you define a sequence X to be equal to the, so you do this for I equal to 1 to infinity, then you get a sequence call this sequence X, define this sequence X to be Xi. Now what we show now is that this sequence Xn that we are looking at, suppose that sequence Xn is Cauchy, we show that this sequence, so the nth component of this Xn actually converges. Ith component of this sequence is convergent. And so essentially what we are saying is this sequence, we expect this sequence Xn to converge to this sequence X defined by the component Xi. So we now show that actually we expect it to happen, but the expectation is different and giving a proof is different. So what are the two issues here? We have to show this X is in LP, first thing. Second thing is this Xn converges to X in LP. What is the meaning of saying that it converges in LP? There are two issues here that you should know. The first issue is there's a component-wise convergence and there's a norm convergence here. That's what I'm trying to put it across to you. Okay. So let me explain to you what I mean here. Okay. So let me open up something. Okay. Just wait. I'm trying to put the PPT on. Just hold on. Just hold for 1 minute. It's the problem with online. We are totally dependent on the computer as well as the network that we have. Just opening, just wait. It is almost opened. So we have a sequence xn. Can you see it? Can you see the screen? You have a sequence xn. Okay. Actually, let me put it this way. You have xn in LP. What is the ith component of this? Xin. Okay. Can you hear what I am saying?
Yes, sir.
Is it seen? Is the screen seen?
Yes, sir.
Okay. Now, what I was trying to tell you is that if you look at this nth component of n minus the ith component of m, so you have this sequence xn. Okay. This sequence is LP Cauchy. That means this LP norm of this is less than epsilon if nm is greater than or equal to n. Okay. So I told you earlier that if you take the ith component of a sequence and take the mod, it is always less than or equal to LP norm of this this one. This I explained to you before. So this will be less than or equal to the LP norm of xn minus xm. This is the ith component of xn minus xm. This is Cauchy. So this implies that this sequence xin, okay, xn is Cauchy. Therefore, this so if you fix this I, okay, and if you look at the xi minus xn, this sequence will be Cauchy. So this will converge. So this sequence xi will converge to some element. So this, you call this as the sequence x, okay. So this will converge somewhere. That's what I was trying to put it to you across. Okay. So the notation is slightly bad in the in this. So this is what I was trying to tell you. The ith component of the sequence xn, ith component of the sequence xn is bounded by the norm of xn minus n. And that follows that this sequence, so you fix this I, okay, for every I, this, you look at the sequence xin. This xin will be Cauchy for every I in n. Since this is a Cauchy sequence, so you let n go to infinity here, okay, I is fixed, let n go to infinity, call this limit as xi. And define a new sequence x equal to this xi. All right. So, is this clear or not? Huh? Should I write it and show you? Hello? Is it clear?
Clear. Clear, sir.
Okay. And call this limit as this. Now, if you look at summation I equal to 1 to n xi minus xim raised to p, this is bounded by the LP norm. That's what we had shown. Okay. And the sequence xn is Cauchy. Therefore, this will be less than or equal to epsilon by 2 if m and n are large. Okay. This is true for all p. And therefore, if nm is greater than n naught, then this summation I equal to 1 to n xi minus xm raised to p is less than epsilon by 2. See the first part and the last part. Now you fix one of the indices. Okay, either you fix m or n. So you take the maximum for I equal to 1 to n mod of this one. This will be bounded by this. This is less than or equal to infinity if p is infinity. For a fixed n in n, you let m go into infinity. Okay, you fix this n in this inequality and you let m go into infinity. So from this inequality, what you get is summation I equal to 1 to n xi and p. So when you take m going to infinity, this xim will go to xi. That's what we have shown earlier. So this becomes xi raised to p raised to 1 by p less than or equal to epsilon by 2. This is true for 1 less than or equal to p less than infinity. If p equal to infinity, you take the maximum and do it, you get that one. So finally, so essentially now you let n go to infinity in this whatever this set one. You get the limit of this I equal to n, 1 to n will go to I equal to 1 to infinity. You get xi and p minus xp. That is nothing but the norm of the x. So norm of xn minus xp is less than or equal to epsilon, less than epsilon. Therefore, you have this sequence convergent in LP now. All right. Now, what I actually wanted to tell you was that so you have the sequence xn. This is in LP. Okay, that is each element is less than a sequence. What we said is that you fix the ith component. So you take this sequence n equal to 1 to infinity. Okay, I fixed. Now we showed that this sequence is convergent. Okay, so now what you do is you call the limit as x. Okay, so you have for I equal to 1, you have x1, you have I equal to 2, you have x2. So this is for I equal to 1, this is for I equal to 2, etc. Now you define, okay, now you define x equal to the sequence, this sequence xi, sequence xi coming from here. Now the claim is that xn minus x in LP narrow goes to 0. We have already shown that the ith component of this goes to 0. As n goes, that is what we have shown here. Okay. This is called point-wise convergence. Point-wise convergence or the nth term convergence. This is called convergence in LP narrow. So what we are saying is, although it's point-wise convergent, it need not imply, okay, the convergence in the norm. But when the sequence is Cauchy, then this sequence converges in the norm also. That's what the point. Okay. Sorry for the sort of delay that I had due to problems of computer. Anyway, that's okay. I'll send you the notes of this one. As far as it's 12:58, so you may have to go for lunch now. So you go for lunch, have your lunch. Essentially, we have to do two things. Is it true that point-wise convergence does not imply norm convergence? That's one thing we have to see. Second thing is whether the norm convergence will imply point-wise convergence. So these two things we will see from 2 to 3, and some examples, we will take into it. Essentially, what we have shown today is that LP for 1 less than or equal to P less than or equal to infinity is a Banach space. Read the material that I have given to you You can also see the book of Lemay. Lemay's book gives you a simpler, better proof. Even the Krajcik book gives you better proof. What I will do is I will give you the material of this from the Krajcik book also. I will send it to you. Read whatever book you want. So in the afternoon, we will take some examples and then see. So what all I am trying to tell you in this hour is that the small LP is a Banach space or it's a complete non-linear space. Okay. Bye. Have a good time. Enjoy yourself. Have your lunch. Rishabh.
Thank you, sir.
Bye.
Bye bye, sir. Yes,
Bye.
yes, sir.
Meet at 2 p.m.